Welcome back to our second video on circular motion. If you're here joining us right now, it is because you have a love for physics that stretches clear across the country. That, or I just said from the first video to join me on the second video, and that's why you're here, because I told you to do so. So either way, welcome! Alright, in the last video we talked about a couple different types of motion with regard to circular motion. We talked about rotational speed, and we talked about, we talked about rotation, we talked about revolution. Then we went on to discuss linear speed, rotational speed, and then tangential speed. So what we're going to do right now is dive a little bit deeper into rotational speed and tangential speed. Alright, I want you to think of a marching band. I want you to think of that marching band as they are making a corner. Okay, so these little boxes are the people in a line, as they're marching, right? They're making that corner and they're turning around in a circle. And let's say we have this many, 1, 2, 3, 4, 5, 6, 7, we'll go 8. Okay, so here is person number 1, 3, 5, and then we'll put person number 8 all the way out at the very end. Okay? And they're turning in this circle, so they are turning, let me get rid of circular motion up here. They are turning in this circle. Okay, so they're going to make a turn. Now, I want you to think of the speeds of these people, right? So how will this look? Okay. Let's talk specifically about the rotational speed and the tangential speed. Rotational speed and tangential speed. Okay. So, you have these 8 people. They're marching, they're walking in a circle, they're playing their instruments, correct? How is their rotational speed going to compare? And remember, rotational speed is like your RPMs, right? The revolutions per minute. Okay? Now think about this. Think about this. Remember, they're revolving. They're going about an external axis. Even though it's called the rotational speed, we're still revolving around that external axis. Okay. And let's look at extremes. How is number 1 and number 8? How will their rotational speeds compare? How does the rotational speed, I'm just going to say RS, how does the rotational speed for number 1 and number 8 compare? How does the rotational speed for number 1 and number 8 compare? Before you answer this, I want you to think about this. Rotational speed is just talking about going in this circle, right? They're just like this, and then they go whoop, just like that. Okay, that's it. So how does that compare? Think about this. Speed is always something per unit time. So let's say that number 1 makes a complete circle. Then let's look at number 8. He makes a complete circle as well. Alright? The time it took for number 1 to make a circle, how does that time compare to the time it took for number 8 to make one circle as well? You are right. They are the exact same time. I know it's kind of weird, but I want you to think about this. So here we go. Let's see, let's try and find the middle of the screen. There we go. So here's middle, right here. So I'm going to turn about this center area right here. I've got person way out here on the end, And I've got this person right here on the middle. You see by the two pieces of tape. One person out here, number 8 we'll say, and number 1's in here. They're going to make one complete rotation. Here we go. Our revolution. Here we go. Right around. We see they're both moving. Number 8's out of frame. He's back in frame. There's a half. Here's number 1. They're still moving in a circle. 8's out of frame. Back in the frame. Boom. Now, they both move the same amount of time. Let's just say 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It took this guy 10 seconds to make one rotation, or one revolution, all the way around. It took this guy 10 seconds to make how many revolutions? 1. They both went around the circle the same number of times for the same time. So I ask you again, how does the rotational speed for number 1 and the rotational speed for number 8 compare? They are exactly the same. They are exactly the same. It doesn't matter how big your circle is. If you have someone right on the inside and someone a mile out on the outside, they're still going to make that turn in the same amount of time. Now granted, this guy is hauling butt. He is moving fast. This one is like taking those little itty bitty steps to go around a circle, while this guy's probably running around in that circle. But they're still going to cover one circle in the same amount of time. Okay? That is their rotational speed. Their rotational speed is the same. Now, let's talk about their tangential speed. And remember, tangential speed is the speed as if you're traveling in a straight line. And remember, a circle is made up of a whole bunch of straight lines going around. For this, we need to think about the distance being covered now. Not necessarily how many circles are being covered, but the distance that's being covered. Let's go back to our friends here. Number 1, this piece of tape, and number 8 way out here, this piece of tape. So there's center. Now let's start back over here again, like we did before. There we go. There's center. It's backwards here. It's kind of weird, right? It's backwards. All right, backwards for me. So here is number 8 way out here. Here's number 1 right here. Look how much distance this guy needs to cover in one circle. In 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Boom. This guy right here just covered this distance right here. That's all he did. Okay? That distance. Now look at this guy. What he needs to cover in the same amount of time, 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Number 8 over here had to cover all of this distance, out of frame, back in frame, all the way down, out of frame, back in frame. And he had to do that in the same amount of time. Yes, I realize that their rotational speeds are the same. They covered the same number of revolutions in the same amount of time. You're 100% right. But their tangential speed, how fast they needed to go in order to do that, is vastly different, greatly different. This guy here can move very, very slow to make that circle, right? Oops, sorry. He can move very, very slow to make that circle. But this guy out here, he needs to really move fast in order to keep up and make that circle. Think about it, right? If you're number 1 and you're on the inside of that circle, you're moving nice and slow. But if you're number 8 and you still need to make that circle, you're running very, very fast. Okay? So tangential speeds, their tangential speeds are different. Okay? Number 1 and number 8 have different tangential speeds. Who has the greater tangential speed? Number 8, because he has to cover more distance. So number 8 has a greater tangential speed because he needs to cover more distance in the same amount of time. Okay, very, very important. I'll let you guys copy that down for a little while. So he needs to cover the same amount of area, or excuse me, he needs to cover a greater distance in the exact same amount of time that 1 gets. That's why his tangential speed needs to be greater. He has to cover more distance. All right, so now comes the time that you all were waiting for, the equations. How lucky are you guys? You don't have to answer. Very lucky, I know. Don't roll your eyes. I know you're rolling your eyes. I can see you. You're rolling your eyes. Don't roll your eyes. All right. So let's talk about equations. And then I think we'll be done. But I don't know. Don't want to make any promises. All right, so as with any topic in physics, we need to discuss some equations because we need to do some math with this stuff. Guess what? There is only one equation that you will ever need to know with circular motion. Now granted, we can get a couple equations off of this equation, but the main equation here is F equals mv squared over r. F equals mv squared over r. I'm going to throw that right over here on our equation board, and I think maybe we're going to put that right over here with circular motion. F equals mv squared over r, which is add another equation. So what does this mean? Well, F is the force. That equals the mass of the object times v stands for velocity. And it's very important, only the velocity is squared. The mass is not squared. Do not square that mass. Don't even think about squaring that mass. No. Only the velocity is squared. And that is all over the radius. So why are we talking about a radius? Remember, we're talking about circular motion. And anytime we move in a circle, we do have, or an arc, we have the radius associated with it. So make sure you square your velocity first, then multiply by your mass, divide by your radius, and you got your force. And we're going to call this F of c for circular motion. Force of circular motion, right? Circular. Ooh, that looks kind of like chocolate. I don't know. Looking at it in the computer screen. That's why we just write C. FC. Force of circle. Okay. So this is the force acting on an object when it's moving in a circle. Alright. Guess what? We can derive some more relationships from this. So let's go back to Newton's second law. F equals ma. And we're going to involve our new equation for circular motion, F equals mv squared over r. From here, F and F are the same. I want you to make this connection, right? F and F, same. M and M, same. M and M, what's up? I'm a rapper. No, just kidding. M, mass, and M, mass, the same. So if F is F, M is M, that must mean that A here is really the same as V squared over R in this case. So from there we can make yet another relationship that we can write over here at the equation board. That, let's see, this was F of c for circular motion. So now we're going to go the acceleration, the circular acceleration. A of c equals v squared over r. So if you're ever asked to find what is the circular acceleration, or what is the acceleration when a car moves around a corner, right there, v squared over r. What is the force acting on the car? Fc equals mv squared over r. There's another little one, right? If you had to find the force, couldn't you just do mass times the circular acceleration if you already have it? We'll go through those in some examples in the next class. Let's keep going. Let's do one more. Let's continue on with this, and we're going to do one more relationship. So from here, we can go, let's see, F equals M d over t squared over r. So what did we just do there? We took our velocity, and we know velocity equals a displacement over time. So we just plugged in displacement over time for velocity. From here, force equals m. Now, moving in a circle, we need to cover the circumference. So the displacement, the distance that we cover, is actually the circumference, 2 pi r, and then we're going to throw in our t, we're going to throw our square back in, and we're going to throw our radius back in. And from here, we can now say that the velocity squared is proportional to 2 pi r over t squared. So if you ever had to find a circular velocity, a car is moving on a circular path, what is its velocity? We could simply do 2 pi r over t. I'm going to put that over here, and we're going to say the circular velocity, I'm going to drop out the squares that I have over here, is equal to 2 pi r over t. So we just have 3 circular motion equations that we derived from one, and its relationship with Newton's second law. Okay, guys, just a little more, and that is it. And we will use all of these equations tomorrow, I can promise you that. Right now, I just want to finish up the way we started with some terminology. And there's 3 different words that people use to describe circular motion. And those are, as you and I would probably say, or we would think, right, centrifugal force. Centrifugal force. Now there's another one that you probably are not familiar with. This one is centripetal force with a P. And the last one, again, you're probably not too familiar with. It's called the centrifugal force. Now, I'm very sad to tell you this, that only one of these forces is real. One is a ghost force, and the other one, it just doesn't exist. Can you guys think which one is the real force, the actual descriptor of all of this that we've been talking about? It is the centripetal force. That is the real force. Real force. The centrifugal force is actually a ghost force. And the centrifugal force doesn't exist. Okay? But that's the term we usually use in society, but it's not real. Right? What we should be saying is the centripetal force. Centripetal. Hey, you went around in a circle, what did you feel? I felt the centripetal force, not the centrifugal. No, no, no. The centripetal force. Okay? And then centrifugal is a ghost force, and I'll explain to you what that means in just a second. But since we know what the real one is, let's go ahead and write down some information about that. The centripetal force, okay, it's any force that causes an object to travel in a circular path. Any force that causes an object to travel in a circular path. So remember from the previous video when I was swinging the mouse around my head, this one, right? There we go. We're swinging that mouse. Now, this mouse is attached by this cord, right? Oops, there we go. This mouse is attached by the cord. So theoretically, it's actually feeling a force of tension. But because it's traveling in a circle, that force of tension is causing circular motion. So the tension force that's felt by that cord is actually the centripetal force. So we could say that F of t, force of tension, is actually equal to F of c, centripetal force. And that's perfectly all right. It is that force that caused the object to move in a circular path. Now, centripetal means center seeking, meaning pointing inwards. And I want you to remember, the centripetal force, the circular motion, always, always, always points towards the center. FC always points towards the center of the circle. Okay, it always points towards the center of the circle. So if we again were looking at this mouse right here, right, and we're spinning him around, right? Something just fell. If we spin this mouse around, his force, let me get in front of a whiteboard. There we go. His force right now is pointing down. The force right now is pointing away from me towards my hand. Right now it's pointing up towards my hand, down towards my hand, over towards my hand. It's always pointing towards my hand, which is in towards the center of the circle, right? It's always pointing towards that center. Because think about it. If that force didn't point inwards and it pointed outwards, this object would just go fly away, right? So it always has to point in towards the circle. Let's see. Without the centripetal force, the object would just fly off in a tangent. So important to remember that. Without centripetal force, the object would fly off in a tangent. We discussed that from the last video. And then the final one is the force always occurs at a right angle to the tangent, meaning it points inwards. Force always occurs at a right angle to tangent. And what that means, I'm going to erase this for 1 second. What that means is if we have this object and it's traveling in a circle and it's attached by a string, the force is always pointing inwards regardless of where it is. But notice, these forces are always at a 90-degree angle to the tangent. Okay, notice they're always at a 90-degree angle to that tangential line. Well, all right, everybody. I think that just about covers our... Oh, no, it doesn't. I forgot to mention to you the centrifugal force. So what the centrifugal force is, that ghost force, that's what you think you feel, what your body feels. Think back to Doris and Rex. When they made that turn, Doris felt like she was moving outwards. That's the centrifugal force, the ghost force that we think we feel as we move out. Remember, that's not true. That's what our body feels. What's actually happening was that door was pushing in and we were experiencing the centripetal force, the center seeking force. It always points in towards the center. And if you hear about a centrifugal force, it's not real. Don't even pay attention to it. All right, everybody. I hope you've enjoyed these 2 videos. We will go over some problems in the next class. I wish you all the best. Have a great day, and I will see you all in the next installment of As the Physics Turns. In circular motion, which allows for the force of a circle to be equal to mass times velocity squared over the radius. And remember that center... You probably already know all this, so we'll just leave it as the physics world turns. All right. See you, everybody. Have a great day. Bye-bye.